All right, let's talk for a moment now about, so there's two different structures, and you guys don't actually need to know the name of this, but it might be easier for me to talk about it as we're going through this. OCN minus and ONC minus. The one on the left there has a central carbon, the one on the right has a central nitrogen. Both of these exist, and I'm just going to go straight and draw the resonance structures for each, and then we're going to analyze those just a little bit. So triple bond, we saw this earlier, O triple bond C single bond N is one good Lewis structure for this polyatomic anion. Another is O double bond C double bond N. And then finally, and this one ends up being the best in this case, O single bond C triple bond N. Well, let's see what Lewis structures that we could draw for a central nitrogen. So let's just follow the same pattern. O triple bond N single bond C. O double bond N double bond C. And O single bond N triple bond C. Again, all of those have a minus charge on them. And in the previous video, we looked at this, so I'm just going to go ahead and write these in for the first set. Okay, so for this structure, positive 1 on oxygen, neutral carbon, and 2 minus on nitrogen. This was the worst structure. No charges on carbon no charges on oxygen or carbon, a minus 1 on nitrogen. And then finally here, a negative charge on oxygen, a no charge on carbon, and no charge on nitrogen. And we said for over here, this one is the best structure. Because it has smaller charges, it only has a minus 1, and then the minus 1 is on oxygen, and oxygen is electronegative. Okay, and then down here, hopefully you can see that some of this is just the same pattern. So 1, 2, 3, 4, 5 electrons around this oxygen. Oxygen element has 6, and so a positive charge. Nitrogen has 1, 2, 3, 4. Nitrogen from the periodic table has 5, so a positive charge on the nitrogen. And then 1, 2, 3, 4, 5, 6, 7. 7 electrons around the carbon in the Lewis structure. Carbon from the periodic table has 4, and so a 3 minus charge on the carbon. This oxygen has no charge. This nitrogen is plus 1, and then this carbon is 1, 2, 3, 4, 5, 6. From the periodic table expected to have 4, so a 2 minus charge on the carbon. And then finally 1, 2, 3, 4, 5, 6, 7. So just like up here, a minus 1 charge on the oxygen, a plus 1 charge on the nitrogen, and then 1, 2, 3, 4, 5 valence electrons in the structure. Carbon atom has 4 valence electrons, and so this has a negative charge on the carbon. So in terms of structures, this has a 3 minus charge in it, so this one's the worst. This has a 2 minus charge, so that one's in the middle. And then this is the best, maybe best of the bad structures. Okay, it has a negative charge on oxygen, a positive charge on nitrogen, and a negative charge on carbon. And so both of these can be made. This compound is very stable. You can beat it with a hammer, hit it with a sledgehammer on an anvil, burn it, do all sorts of things to it. This one is not explosive. This one is explosive, and as a silver salt, this is the compound that is in the snap pops that you'll see around the 4th of July. The small little bags that you throw and they snap on the ground have this in there as an explosive. And so just by drawing these simple structures, comparing the best in each case, it gives us some reason why we know that we want to minimize charge as much as we can. This structure allows us to have a -1 charge only on oxygen. Here we get that, but we also have to put a positive charge on one of the atoms and a negative charge on one of the atoms. And this is all flipped around from what we would like. If we had to put a negative charge, it would be better to be on a nitrogen atom, because nitrogen is more electronegative. So we've put a negative charge on carbon, and carbon really doesn't want. We put a positive charge on nitrogen, which nitrogen really doesn't want. And so this structure is significantly worse than this one, and helps us to rationalize why this is an explosive polyatomic anion, and then this one is a very stable one.